Okay, YouTube, this is my first video for my Algebra 3 prerequisite chapter number 4, in which we're going to be discussing really the basics of polynomials, including what they are, a certain vocabulary, as well as how you add, subtract, multiply, and really kind of, I guess we'll save division for later, but add, subtract, multiply with them or operate with them. So let's go ahead and start by how we define what a polynomial is. But a polynomial is a single term or the sum of two or more terms containing variables with whole number exponents. So essentially, you'll see this a lot, and the coefficients, we say this is a polynomial here. We say the coefficients would have to be real number coefficients, but you'll notice it's just a bunch of terms written in, I guess you could rewrite this here as a sum of terms. You could always rewrite any subtraction as adding the opposite, but basically it has many terms, and the exponents are whole numbers on the variables, but we would consider that to be a polynomial. And I always kind of remember it this way, but when you hear the prefix poly, it just, it infers that we mean many. So we say a polynomial is a many-termed thing. So a polynomial, okay, is a many-termed thing, expression, where we have whole number coefficients and real number coefficients and whole number exponents. But again, let's go ahead and consider this one right here. I just do want to point this out again. We can express any polynomial is purely the sum of terms here. This one happens to have 4 terms on it. We can change it to all addition if you prefer to do that. A lot of people just leave it as subtraction if there's any subtraction between 2 terms. Moving on, the degree of each term is the value of its exponent, okay? So when we look at a single term here, we say some ax to the n power, where n is some whole number here that's positive or at least non-negative. We would say that the degree of this term here is just n, where a is not 0. We say a is our coefficient of this. If a were 0, basically 0 times x to the n would just be nothing in the first place, and you wouldn't have a polynomial, really. Or at least you would. It'd be a very boring one. But we say that the degree of ax to the n is just n. And we also note here the degree of a non-zero constant is 0. So that constant 0 has no defined degree. That is, if I were to say, well, here's my polynomial function, it's just 7. It has one term, just that. You could really look at this as 7 times x to the 0, where 7 times x to the 0 would really be 7 times 1, which is 7. So we would say that any constant term, if it's just a constant, that term has a degree of 0, whereas, this term up here would have a degree of 3, this term has a degree of 2, this has a degree of 1, and again, this negative 6 here would have a degree of 0, but every term has a degree in a polynomial, okay? So, for instance, again, down here, you look at this example that I've kind of copied and pasted in here, but we say 6x to the 4th minus 3x cubed plus 2x minus 5. This term has a degree of 4, this term a degree of 3, this term actually has a degree of 1. We don't write that exponent, but we assume it's there. And this non-zero constant term has a degree of 0. So it is also important to note that the degree of this entire polynomial, we consider the degree of the whole polynomial to be the greatest degree of all of the terms in the expression. So whereas we were to look at this polynomial expression up here, we say, well, what's the greatest degree on any term? We say it's third. So the degree of the entire polynomial is, we would say it's a third degree polynomial, whereas this one down here, since the greatest exponent on any of these terms, the greatest degree on any of these terms is 4, we would refer to this as being a 4th degree polynomial, okay? And then the last thing I want to kind of mention here before we move on to these examples is essentially, you'll notice that in each of these polynomials that I've listed here, that the exponents are listed in descending order. And we kind of say that that's pretty standard, so standard that we refer to it as standard form. So when we talk about the standard form of a polynomial, we refer to it being listed so that the exponents are in decreasing order, and then we can easily see that the degree of the polynomial is going to be the exponent on the leading term up here, and we refer to this front number here, this front coefficient, as the leading coefficient. So what I'd like to do before we define polynomial in x in general is essentially this. Let's take all of these polynomials that I've listed here, a, b, and c, and what I'd like to do is list them in standard form and also state the degree of the entire polynomial. We don't need to state the degree of the terms, but of the polynomial. So you'll notice here we have negative 2x to the 4th plus 5 plus 2x to the 5th. If we were to write this in standard form, well then we would need to start with 2x to the 5th since it has the highest degree of any other term. So we say 2x to the 5th. I'm going to write this as plus a negative 2x to the 4th. Okay, I'll write it that way. Suppose we could. Plus 5. And you don't have to write the plus. You can just write minus 2x to the 4th. But we would say the degree of this polynomial, degree is 5th degree. It is a 5th degree thing. And I don't like that 5, so I'm going to rewrite it. 5th degree is the degree of this polynomial. Okay. Looking at letter B here, you'll notice that we're not using x, and that's totally fine. We could have a polynomial in the variable y. But looking at it, it seems that the highest degree is already in front here. We have 2y cubed, followed by this plus 3y squared minus 2y. I'll just go ahead and write a negative sign here and express it as subtraction plus 10. Okay. So we have a 0th degree thing, a 1st degree thing, a 2nd degree thing, a 3rd degree term. But basically we would say, because this is the highest degree, we would say that the degree of this polynomial degree is a 3rd degree polynomial. Okay, and then last but not least, the square root of 8 plus a to the 6th. This is a polynomial in the variable a. But we'd say this is really a to the 6th plus the square root of 8. Now, square root of 8, it's not a variable. This is a constant. So this would be a 0th degree term. This is a 6th degree term. So again, we do want to list the degree of these polynomials. And in this case, we have a 2nd degree. Oh, I was just thinking too, because it has 2 terms. This is a, of course, 6th degree polynomial. So the last thing I want to mention before we get on to this definition here is this. When we have a 3-termed polynomial, we tend to refer to these things as a trinomial just because it has 3 terms. Whereas something down here, I bet you could guess, is a binomial polynomial. Now, if it has 4 terms, this is interesting. Is it called a quadnomial? I always get some good guesses on this one. But if it has, 4 or more terms, we could just call it a four-nomial, okay? And it is worth mentioning that if it has 1 term, 1 term, this would indicate that it is a monomial, okay? So if I had a polynomial where its f of x equals 7, that would be a monomial polynomial, okay? Monomial expression. So now down to our definition of a polynomial in x, and then we'll talk about how we add, subtract, and multiply these things. But when we define this polynomial in x as an algebraic expression of this form, the first thing I want everybody to notice is that all of these a's here, these a's that are connected to the x's, we have an minus 1, an minus 2. The thing I'm really trying to point out here is when we write these little things here, we refer to this as a subscript. And I want you to know that that has nothing to do with like exponents, okay? We basically just write the subscript to say that this a sub n is really the coefficient of the term that has n for its degree, okay? And a sub n minus 1, well, that is the coefficient of the term that has n minus 1 as its degree. And if we said, well, what is n minus 1 and how is it significant with respect to n? Well, if n is, say, 7, well, then this one here is going to be 7 minus 1 is 6. And if this is, say, n is 7 again, this would be 7 minus 2 is 5. Basically, what this is indicating is that it's going in decreasing order. And you notice that this will continue on all the way down to our coefficient of the degree 1 term plus coefficient of the degree 0 term, which I guess we could write a sub 0 x to the 0, which is really just multiplying by 1 anyways. But this is what we refer to as being a polynomial. And I do want to point this out. We say a sub n minus 1, a sub n minus 2, all the way down to a0. They have to be real numbers. And we also say this, a sub n cannot be 0, okay? We refer to this first number here as not being 0 because if it were 0, well then this whole term here would just drop out anyways. So we're reluctant to call any of these zeros, especially the first one. Furthermore, we say n is a non-negative integer. So again, we say that these n values, these exponents, they're not decimals and they are not negative. So they're just really whole number exponents, okay? So we say the polynomial is of degree n. Why? Well, because n was the largest degree of any of the terms. And this is very important. We say a sub n is the leading coefficient and a sub 0 is the constant term. So we'll make a little note here. This is always going to be a constant if it is 0th degree. And a sub n, we refer to this guy as the leading coefficient. And, I'm going to abbreviate that as LC, leading coefficient. Why is it the leading coefficient? Well, it's the coefficient that leads everybody else. So, pretty self-explanatory. So let's go ahead and take a look at some addition and subtraction with polynomials. Now, when we add and subtract polynomial expressions, all I'm saying here is that what we're going to do is we're just going to combine like terms. So I've just given a couple of I guess, expressions here. The first one is going to be a sum, and the second one's going to be a difference. But what I want to do is just combine like terms. Now, it is worth noting that these are not the same problem, not the same polynomials in each case, so let's be careful. And also this. I've put the polynomial expressions in parentheses. So, for instance, here we have some four-nomial that is 3rd degree, okay, the whole polynomial is 3rd degree, plus some other four-nomial that's 3rd degree, and we want to add these things together. And since we're combining like terms, we don't really need the parentheses. So we could drop the parentheses, and really what we're looking at here is we can take this negative 17x to the 3rd and combine like terms with the 16x to the 3rd, and, well, what do you get when you have negative 17 and a positive 16? We get negative 1. So we really get negative 1 of these x to the 3rd things. And I'm just going to put a little check mark here just to note that we've done those. Taking a look at our next terms that we can combine here. We have a positive 4x squared and a negative 3x squared. Well, a positive 4 and a negative 3 of something gives us 1 of something. So we have positive 1 of these x squared things. I'll put a check mark on those. Let's go to our x to the first terms. Negative 11, positive 3, that's a negative 8. So we have negative 8x to the first. And then last but not least, we have negative 5 as our constant on the first polynomial, negative 15 our constant on the second. When you combine like terms with those, you get negative 20. So basically, we added a third degree to a third degree, and we got a third degree polynomial. And there it is. I mean, there it is, okay? Now, subtraction. Thing is, recall that I wrote on the front page that this is like some hypothetical polynomial making up, like 2x squared minus 2x plus 5. I just made that up. I made it up, you guys. I said that we could rewrite this as a sum of negatives if necessary. Notice how I kind of took this negative and I rewrote it as adding the opposite, okay? Basically, we could take the same, tact here and say that really what I want to do is I want to add, change this to addition, a negative 1 times all of this stuff inside the parentheses here. And the thing that I'm really trying to point out is when you have a negative in front of an entire quantity, what you need to do is you need to distribute that negative all throughout that quantity. So I'm actually going to take the time to rewrite this entire set of expressions here, but we have 13x to the third minus 9x squared minus 7x plus 1. There was our first quantity. And as I distribute the negative throughout this second quantity here, we got a negative 7x cubed, so I have a positive 7x cubed there, a negative positive 2x squared, so we get negative 2x squared, a negative 5x, which is a positive 5x, and a negative positive 9, which is a negative 9. So again, really, this just becomes addition. That's all we really have done when we changed this to this. So doing this with the same kind of process here, we're going to say 13x to the third, 7x to the third, that's 20x being cubed, x is being cubed. In terms of x's squared, I have negative 9 here and negative 2 here. It's negative 11 total x's squared. If we were to talk about our x's to the first, negative 7 and a positive 5 is negative 2 when we combine those two x's to the first. And last but not least, our constants here. We have positive 1 and negative 9 is negative 8. So this would be our polynomial difference in this case. We subtracted a third degree from a third degree and we got a third degree. So the last part of this is kind of just an introduction to how we multiply polynomials, where I've actually just copied in and pasted a couple of examples here, and then we'll talk about doing a few on our own here, a couple on our own. But when we multiply polynomials, it says we have to use the properties of exponents, okay? Recall that when you take, say 7x squared times, 3x to the fifth, you start by taking the coefficients times one another, and then you really just say, well, x squared times x to the fifth, we would just say x to the 2 plus 5. That's just our rules of exponents. So we'd really get 21x to the 7th, okay? That being said, we're going to use these properties of exponents, but along with distribution, okay? So I'm going to consider these two trivial examples. The very first one is this. If this, says that we're taking negative 8 to the 6th, 8x to the 6th, and taking that and multiplying it by 5x cubed. Again, we take negative 8 times the 5 first and get this negative 40, but we add the exponents on our x's here because we're multiplying two things with the same basis. Really, we're saying in effect we have 9 total factors of x being multiplied together, okay? So you multiply the coefficients and add the exponents. Likewise, down here, we have a monomial thing, 3x to the fourth. We could put that in parentheses, actually, if we want to. 3x to the fourth times this trinomial here where we have a 2x cubed minus 7x plus 3. And you'll notice that, they put these little rainbow symbols on here. We're doing the same thing we just did up here, except for we're distributing it throughout the entire quantity. And we must do that with everything that is listed in here. And so once we've done this, it's kind of worth noting, if you took 3x to the fourth times 2x to the third, we had a fourth degree thing, times overall, a third degree thing here. If you were to take the highest degree here and the highest degree here and multiply them, when you add those exponents, you're really going to get something to the 7th. So it's kind of worth noting that if you took a third degree times a fourth degree, or a fourth degree times a third degree, you get a 7th degree polynomial. In this case, we turned out a trinomial here, okay? So looking at these examples down here, I'm going to actually kind of block off this foiling method business first. There, that looks a little bit better. And we'll take a look at this first. We have a binomial times a trinomial. And so I don't want to throw anybody off here. Basically what we're going to do is the same thing we just did with distribution, but the thing is everything on the left over here in this set of parentheses has to be multiplied by everything on the right over here. So when I put in this arrow here and this arrow here and this arrow here, I'm saying, well, I got to take 5x times 5x to the first times 3x to the second. And so we get 5 times 3 is 15. We say x to the first times x to the second is x cubed. Okay. Now we're going to take the 5x times negative 5x. Well, then we get negative 25x to the second. 1 plus 1 is 2, of course. And then 5x times a 4 here, we're going to get 20x's. Once we have done that multiplication there, we say that the 5x is exhausted. No, literally, we say that way. We say we've exhausted all possibilities. So we say now what we're going to do is move on and take this negative 2 here, and I'll even switch colors for us. And we're going to multiply it by all of these things as well. So we say negative 2 times a positive 3x squared is a negative 6x squared, and negative 2 times a negative 5x is a positive, and we get 10x to the first, and negative 2 times a positive 4 is negative 8. So what you look at here is, it is the product of these two things. And it makes sense that you took a binomial times a trinomial, and we had to multiply 6 total times. But the fact of the matter is we need to simplify whenever we can. So we'll take this 15x to the third. There are no other x to the third degree, third degree terms here. So we'll just say we've got that. If we were to take this second degree term plus this second degree term, negative 25 and negative 6 is going to give us negative 31 of these second degree x's here. A positive 20x to the first and a positive 10x to the first is going to give us 30x, and then we have negative 8. So this is our final product here, okay? And it's worth noting you took a first degree thing times a second degree thing, and you got a third degree thing. So the last thing we want to mention here is this, it's a classic, you guys. It's withstood the test of time since probably you were in 7th grade. But multiplying two binomials, we refer to this as the FOIL method to multiply binomials, which FOIL essentially stands for first, outside, inside, and last. And so when you multiply two binomials such as this, it's really the same thing we just did. We'll take everything on the left times everything on the right till it's exhausted. But multiplying the first two terms really means that. We're going to multiply the first two terms in each set of parentheses. So we start by saying, for example, I'll take the 7x times the 4x here, and I get, 7 times 4 is 28, and x times x is x to the 1 plus 1, which is x squared. Moving on, though, we say, well, now we'll multiply the outside two terms, which really means that as well. We say take the outside times the outside. And so I'd get 7x times negative 3 here, and I'd get negative 21x. So now moving on to our inside two terms would be this negative 5 and the 4x here, kind of like it lists here, the inside. We say that would be negative 20 x's, and then last but not least we would do the last two terms after we've done that. So we say negative 5 times a negative 3 is a positive 15. And again, if you can simplify, you certainly always should simplify. I know that combining like terms here, we get a negative 41 of these x things plus 15 constants. So this is our second degree polynomial that we got as a result of a product of a first degree with another first degree. Cheers.